In the last video, we introduced a new notation, the definite integral. The definite integral is a way of indicating in sort of a compact notation that I want to find the area under a curve between two certain input values. And if I know some sort of geometry that can help me, I use it. If I don't know geometry that can help me, I either make an approximation or I wait for 5.3 and learn the secret. It's coming up soon. But for now, we have one little piece to add to this understanding of a definite integral. I have an example here. What is the value of the integral from -1 to 4 of f of x dx? And I can see I've been given a picture of f of x. And all the shapes here are shapes that I recognize from geometry. I see two trapezoids. If you see a bunch of triangles and rectangles that you can add together, that's just as good. Feel free to break up an area in whatever way works for you. But know that you're going to be able to get an exact answer here because these are straight lines, and we can use these line segments to form areas into trapezoids, rectangles, or triangles. What's new here is that whenever my curve that I'm trying to find the area underneath falls below the input axis, in this case the x-axis, then the areas that fall below the x-axis are considered negative and must be subtracted out. So when I look at this picture, I see a, it's not really technically correct to call it a positive trapezoid. I see a trapezoid that lies above the x-axis. I'm going to shade it in a little bit. Maybe you see a triangle and a rectangle and a triangle, both totally fine ways. I also see a trapezoid that lies under the x-axis. If I don't think anybody's listening inside my head, in my head I call it a negative trapezoid. It's not really negative. It's a trapezoid whose area I have to consider negative. But this is what I'm talking about. And notice, sometimes when we say we're looking for the area under a curve, that's not specific enough. You're looking for the area between your function curve and the x-axis, or whatever the input axis is. When it's time to evaluate this integral, I am going to take the area of the trapezoid I shaded in blue, and I'm going to subtract away the area of the trapezoid that I shaded in red. I made that picture because I thought it might be helpful. That picture would not get you any points on the AP test, but if that helps you to think through what math we need to do next, feel free to use it. I'm going to find the area of the trapezoid I shaded blue. I'm going to find the area of the trapezoid I shaded red. I'm going to subtract the positive area trapezoid minus the negative area trapezoid. So for me, when I think about this, again, if you're going to think of this as two triangles and a rectangle, that's fine. Do that, no problem. I like practicing trapezoids, so I'm going to find the two bases and take their average. The top of this trapezoid has a length, that distance across of 1. Across here, that's 1, 2, 3 spaces. Take the average of the bases and multiply by the distance in the other direction. In this case, that would be the height. Minus, when I look at this tiny red trapezoid, I see two bases. That has a distance, well, I should have changed to red, huh? That has a distance 1. This is a distance of 2, so I'm going to take the average of the two bases and multiply by the distance in the other direction. That's the height. So you have two options at this point. We could have thought we were adding the areas together, but in that case I would have had to think of that height as a -1. We're going to end up subtracting, doing the same calculation. So again, feel free to leave your answer unsimplified. I notice that I can simplify here, and I'm going to get 4 minus 3/2. That's 8/2 minus 3/2. My final answer, 5, that's 5/2. 5/2. So the integral from -1 to 4 of f of x dx is 5/2. So now we're going to start to see more and more interesting functions in your integrand. So far, if we have a linear function as our integrand, we know we're going to make a trapezoid and we can find the area. If we have one of those crazy half circle functions, then we can use what we know about circles to find the area. We want to get to the place where we can have any function we want as the integrand, and we'll know a way to find the area, even if it's not something we recognize from algebra. So we're going to start to work through another family of rules that we can use. This first rule is cool because it has a geometry. It's going to make a picture that we recognize totally from geometry, but we're going to see how it helps us connect to where this whole other set of rules for evaluating integrals is going to come from. So, if you need to take the integral and your integrand, the function inside the integral, is a number, it's a boring function, it's a constant function, then you can use this expression to find the area all the time. The c, whatever that constant function was, times the difference that you get when you subtract the top limit minus the bottom limit. I don't need you to memorize that because I think if you see the picture, you'll understand where it comes from. So I'm going to do this example. This says the integral from -2 to 1 of 5. So I'm going to imagine what that looks like. Here is a graph. I'm going to graph the constant function 5. Well, that's easy. That's a horizontal line at 5. I should have made it go farther back here. And I'm supposed to find the area under this curve between -2 and 1. So if I try to color that in, between -2 and +1, the area under the curve, the area between the 5 curve and the x-axis. What shape did I make? I made a rectangle. No problem. So what's the height of the rectangle? 5. How wide is the rectangle? Well, it covers a horizontal distance between -2 and 1. I can either count spaces or I can subtract. 1 minus -2 makes 3 spaces wide, and my area is going to be 15. Look at this. That was my constant function 5 times my top limit minus my lower limit. But all this does is sort of formalize a formula you could memorize for finding essentially the area of a rectangle. So how high is your rectangle going to be? Well, it's whatever your constant function was. How wide is it going to be? Well, it's going to be the top limit minus the bottom limit. That's going to be your horizontal distance. So this second example is kind of the same thing. It's just slightly more interesting numbers. If I want to integrate radical 2 from radical 2 to radical 18, here's my picture. I have a constant function, y equals radical 2. And I want the area between radical 2 and radical 18. I can get a different color here. What kind of shape have I made? Imagine those lines are straight. Again, I've made a rectangle, so the area of this rectangle is going to be the height of the rectangle, which is the constant function value, radical 2, times the difference between my two x values. And I can tell that's a positive, like I have a positive width of my rectangle, so it must be radical 18 minus radical 2. Uh-oh. It's been a while since I've simplified an expression like that, but watch what happens. I'm going to multiply, this is going to be the square root of 36. That's square root of 2 times square root of 18. The 2 and the 18 can multiply together. And my radical should go over the top. Minus radical 2 times radical 2 makes radical 4. If you were all interested in simplifying this answer, square root of 36 is 6, minus 4, minus square root of 4, 6 minus 2. Final answer is 4. And really, the thing to notice here is that this expression I wrote is equivalent to this little rule that you're welcome to memorize, or you're welcome to do what we've done here.